I'm a second year PhD student at IAS. I'm working under the supervision of Nabila Ghanim and Mathieu Wenger. And so I will present to you my first paper that was submitted a few months, 2 months ago, which is called Populations of Filaments from the Distribution of Galaxies in Numerical Simulations. And there you have the archive number if you want to follow with me. But I put the plots in the slides anyway. So yes, I will give you an introduction about what's the cosmic web and what's the current state-of-the-art research on filaments, and then I will move to my results. So I don't know what is your background on the cosmic web, so please don't hesitate to ask questions at any point of the presentation if you don't understand or if you have more comments to give. So we know that matter in the universe is not distributed uniformly. It follows an isotropic structure that is the cosmic web. So galaxies are assembled into groups, and it's too bad I cannot point you cannot see my my cursor. Well, galaxies are assembled into groups, and groups are into clusters, and clusters of galaxies are connected between them to form a filamentary structure that is the cosmic web. So the easiest way to see this cosmic web is thanks to observations of galaxies, and that's actually how we detected the cosmic web in the first place. So this is the plot from the Lapparent, and so in this plot, each point is a galaxy, and we can clearly see that the filamentary structures are there. And the other plot from a more recent observation, which is SDSS. So so it's lower right part of the slide, I plotted a slice of a simulation, and there we can clearly see the structures of the cosmic web. So we have filaments, clusters, and voids. So blue. Sorry, in purple we have dark matter, and the red points are galaxies that follow the skeleton of dark matter. Yes, what's interesting about the cosmic web is, especially what for me is our filaments, because this is what I am studying. Thanks to some studies performed on simulations, we have we can say that half of the mass of the universe is contained in cosmic filaments, which is amazing. And also on the left part of the plot, we can see the distribution of dark matter for the different structures. So for example, in yellow we have we have the nodes. So we can see that they are clearly the most dense structures in the cosmic web. And we can see that filaments have a very broad distribution that cover almost 5 orders of magnitude of densities. So we have filaments that are as dense as clusters, and other filaments that are less dense, like maybe into voids. However, filaments are not very studied because they are very hard to observe. And well, now I will tell you a bit what's the current knowledge that we have on cosmic filaments. We can study them either by performing dedicated studies. For example, this is something that is done in my group at IAS. So very recently, Nicola Malavasi studied the connectivity of the coma cluster And he found that this cluster was connected to the cosmic web by at least 3 large scale filaments. And also another dedicated study is the filaments between the cluster pair A399, A401. And this is a cluster, a filament that has been broadly studied with very multi-wavelength observations, and people have tried to characterize this filament that has a very high density, and galaxies there are mostly quenched, so it's a very particular filament. Another way to abroad the study of filaments is by doing statistical studies. But to do so, we need first to detect the skeleton, the filaments. And to do so, we need algorithms to detect them from the distribution of galaxies or the dark matter particles if we are trying to get a skeleton from the dark matter. And there are a lot of detection algorithms in the market. I used DisPerSE, so I will introduce what DisPerSE is further in my presentation. And Tony, which is another PhD student of my group, is developing his own detection algorithm based on graph structure and on trees. So this is his T-Rex filament finder that we can see here. And these statistical studies are mostly focused on the properties of galaxies around the filaments, and not on character. The aim of these studies has not been to characterize the filaments as structures, but rather to focus on if the galaxies are most star forming or less star forming at the core of the filament or at the outskirts. So a global picture of filaments is still lacking. And this is what is my goal of mainly my PhD thesis is characterize the cosmic filaments. And in this paper, we used the galaxy distribution and simulations. So why galaxies? Again, because they are the most easily observed and they trace the dark matter density field. And my goal was to answer to these questions. So how is the matter distributed around filaments? If this distribution depends on the properties, the relation with the environment, and if we can model this, the distribution. And I will focus on the universe today, so at redshift 0. So the main 2 ingredients of this work are first numerical simulations. So I used 2 different numerical simulations. Why 2? Because we wanted to have simulation independent results. So I used TNG and MAGNETICUM, which are have different cosmologies, have different resolutions. And I selected the galaxies according to stellar mass criterion to have galaxies that agree with observational limits. Then I applied this detection algorithm to the catalog of galaxies to get the filaments. So DisPerSE is it's an algorithm that first computes the density field from the galaxy distribution, and then detects the filaments based on the topology of this density field. So basically, filaments are a set of segments that go from a maximal density critical point. So in red here in the schema. And these segments go from the maximum density critical point to the saddle of the density field. So the histogram that we have here is the length distribution of the filaments of TNG and MAGNETICUM simulation. They show an exponential tail, which has something that has already been seen with filament length, so it's good. And in the following, as we want to focus only on the contribution of filaments, we decided to remove from the catalog of galaxies the contribution of galaxies that are in the densest regions of the cosmic web, that are the clusters. So yes, let me now show you what some of my results. So I computed an average density profile of galaxies around the filament. So basically what I did is I counted the galaxies in concentrical cylinders that were aligned with the axis of the filament, and then I divided this number by the volume of the cylinder, and this is what we get. In the left part of the plot is the core of the filament. So we have a low R, low radial distances, and towards the right we get far away from the filament. So first I will explain to you the blue curve, which is the null test that was done in order to prove that or to test the method. So it's flat, so we can say that the method is not biased. And so the black curve is the signal itself of the galaxies around the filament. So we can say that there's a significant excess with respect to the background density, and that we have a signal up to 27 megaparsec away from the filament. So what happens if we do the density profile of the other simulation? So it's the pink curve here. I rescale the background so we can compare the curves, and we can see that the two profiles are very similar. And we perform Kolmogorov-Smirnov tests that shows that indeed there's a probability that they come from the same distribution. So yes, these plots characterize the total population of filaments. So we mix together every kind of filament of the catalog, and we wanted to see if there's a dependency on, for example, the length, properties of filaments, for example, the length. If the density depends on the length of the filament. So to do so, we separated the catalog of the filaments in different bins of length. Each bin had the same number of filaments, and this is what we have. So filaments of different lengths have significantly different radial galaxy densities. Short filaments, which are in yellow in this plot, have higher density values at all radial scales, and when the density decreases for long filaments, which are in blue. I wanted to quantify this difference, so I computed the deviation from the average profile, which is in dashed black dashed lines in the profile. And this is shown in the lower panel of the plot. Thanks to this deviation, we separated the filaments into two populations, the two extreme populations that deviated the most, and that are the very short filaments, which are shorter than 9 megaparsec, and very long filaments, like longer than 20. So I computed the average density profile of all the short filaments and of all the long filaments, and we wanted to test the statistical properties of these density profiles. And to do so, I first computed what I like to call a bootstrap KS test, which is basically I compared the density profile of the short population with a random extraction of random realization of density profiles taken from the complementary population. And I did that 1,000 times in order to test, to have a distribution that takes into account the properties of the complementary population. And so we did that for short and long, and the resulting p-values were very tiny, showing that the profiles of each population cannot be randomly reproduced. And then we directly compared the short with the long, and we had a p-value of the order of 10 to the minus 11, showing that these populations, short and long, are indeed two different populations. So this is what how the profiles look like. So in solid lines, we have the TNG simulation. In dashed lines is the MAGNETICUM simulation. So before going into explaining the similarities and the differences between these profiles, I will give you some scales that we can see here. So first, the radial extension. So it's basically the radius for which the density reaches the background density is 20. I cannot see this. Sorry. Yes, so the radial extension is higher for short filaments and for long filaments. It's almost twice the value. And I computed an R2 radius, which is basically the radius for which the density is twice the value of the background. And the same trend was observed. So short filaments are short and a bit fat, puffy. And long filaments are long and thin. They are less extended than short filaments. If we focus on the long filaments, so we can see that they are remarkably compatible with at radius higher than 1 megaparsec. However, at the core of the filaments, the profile of MAGNETICUM simulation is a bit shallower, and we can wonder if that comes from a resolution effect, because actually the MAGNETICUM simulation is 17 times less resolved than the TNG. However, the short filaments are very different, and at this stage we had the intuition that actually these filaments are not in the same environment than the longer filaments, and we have the intuition that this might be short filaments might be in over-dense regions, and in these regions the subgrid physics of the simulations are very important, and they determine the distribution of matter. For example, the AGN feedback and this kind of stuff can influence a lot on the distribution of matter. So that's why we wanted to quantify, to study the environments of these two populations. And to do so, we first computed the excess of density. So it's basically the profile, the density profile of the filaments, which has been integrated up to a certain radial scale. So we decided to integrate up to 2 megaparsec. And this is the distribution of excess of density that we get. So we have different density distribution for short and long filaments, and long filaments seem to be less dense than, statistically less dense than short. And if we focus on the range that is shown by this distribution, excess of density distribution, we can compare it with the first plot that I showed you in the introduction, and we see a large range of densities as well. Then we computed the mass of the maximum density critical point to which the filament is attached. So using dark matter particles, we computed this mass, and we see that short filaments are statistically connected to objects that are more massive than long filaments. And so if we combine these results, we can say that short filaments are in over-dense regions, as we had the intuition, and long trace less dense regions. So this gives us a picture of short filaments that actually might not correspond to to the cosmic filaments that shape the structure of the cosmic web. These short filaments might rather be in overdense regions that are maybe acting like bridges of matter between overdense structures in these overdense regions. To finish, so we wanted to try to model these densities and the density profile, and to do so we took some models of the literature. These models are inspired on cluster literature, the generalized Navarro-Franken-White, the beta model, IAS-Orsay profile, and a single and double power law, which are more empirical models. And we fitted these models to the density profiles of short filaments and of long filaments, and we fitted also the total population. And so this is the plot that you see here is the result reduced chi-square. So in this plot, we can see that short filaments and long filaments are better fitted when they are taken separately than when they are mixed together, as we expect from two different populations. And we also see that the GNFW, the beta model, and the single and the double power law are equivalent. They perform well, but the IAS-Orsay model is not adapted to fit these density profiles. And here we can just see some corner plots of the MCMC exploration of the parameters, for example, for the double power law. And the profiles there are the resulting fitting curves of GNFW and the double power law that match quite well with the data. And yes, that's the end. So to conclude, yes, we computed galaxy density profiles, and we studied the relation of this density with the filament length. And basically, we found that that we were mixing two different populations, the long and the short and the long. So the shorts can be seen as short and puffy filaments that are connected to denser, more massive objects that may correspond to bridges of matter, and therefore their dynamics can be dominated by gravitational forces of collapse because of the environment where they lie on. On the contrary, long filaments, they are very long and thin, they are less dense, they are connected to less massive objects. These are the filaments that may correspond to the cosmic large-scale filaments when we think about the cosmic web. And they can be dominated by different dynamics than the short population. And for example, the dark matter forces that stretch the cosmic web, and these two populations can be living and dominated by different kinds of forces. And yes, we tested empirical models, and I think that's it for me. Mm-hmm.
Thanks a lot, Daniela. So are there questions?
Actually, I have a question on the plot with the short and long filaments. There was a few slides before.
Yes.
It's just
this one.
Yes, you were showing that exactly in the long filaments they are matching, starting from 1 roughly megaparsec. Yes. I was wondering, yeah, exactly. I don't know, maybe you said it, but I couldn't understand whether there is instead an explanation of why the short ones are not matching.
Yes, so that's where we think that maybe the shorts are not matching because TNG and MAGNETICUM are different simulations that have different I don't know how to say, the recipes for the subgrid physics, for example, for the star formation, for the AGN feedback, and these recipes can can be responsible of the difference between.
What does that mean? A subgrid physics? I mean, what kind of physical parameter is like unknown in there?
The model, for example, of the efficiency, for example, of AGN feedback can be one of the parameters that might explain this difference. Also, these two simulations have different cosmologies, so this is something as well that we have to test if this is cosmology dependent.
And the blue ones are also for different cosmologies.
Yes, the blue ones are again for the same two simulations, so TNG and MAGNETICUM. So the TNG has the cosmology of Planck 2015, and MAGNETICUM has a WMAP cosmology.
Okay, thanks.
I have a question.
Yes.
Thanks for your talk first. It was nice, very nice. I have first a question about the accuracy of the method. So you have a method to estimate filaments. So how accurate it is. So imagine that you know the distribution of filaments. How well can you recover the distribution? And the second question is, you mentioned that you are a colleague or PhD students who is developing his own new method. So the reason is, why developing a new method, and what do you expect more from this new method?
Yes. So thanks for your question, because actually the method of detection of filaments is, I mean, it's a nightmare because each method depends on their own physical parameters. So you have methods that use the Hessian of the density field, other methods that as DisPerSE that use the topology of the density field. You have other methods that detect filaments based on the distribution of velocities of the matter, and so as we don't have a clear picture of what the filaments are, how can we can define filaments? So we can just keep doing methods and trying to fine tune parameters to have skeletons. So yes, of course, these results are for the moment are dependent on the method that I use for defining the skeleton. So what we're doing right now is collaborating with another group that has developed a method that is called Nexus, that is not publicly available for the moment, and they define the.
Which group?
Sorry.
Which group?
It's a group in Leiden with Rin
okay.
van der,
yeah, I know the, yeah.
And Marius Schouten. So yes.
Mm-hmm.
And this sorry, I got lost. Yes, so to answer your question, so T-Rex is a method that does not want to have like free parameters, and it basically it fits a probabilistic model to the galaxy distribution, and then it builds a graph, and the filaments are defined as the edges of the ridges of this graph, and yeah, so T-Rex has a probabilistic approach to the skeleton. So you can have basically a filament associated with a probability of, okay, this is a true filament or maybe not.
But whatever the method that you are using, do you have a kind of simulation where you know exactly the density, where you can evaluate the quality of a method, whatever it is? Because here I'm the thing that you are using a method, and then it produces something, get something out, or it looks like it's useful, but you don't know how accurate it is.
Yes.
Then you can replace this method by another one, but you will have exactly the same problem, right? It's not,
yes.
it's not because you have a probability that this probability is correct. Okay, so the question is the accuracy of the measurements provided by your method. And this you could try to get it through a kind of a toy model. I don't know. Imagine that you build yourself a density of filaments plus some clusters, and then you run it and you see what you get out.
Yes, that's true. So this is something that Tony's Tony, the developer of T-Rex, is working on, trying to. The first part of his PhD was to compare different methods and to try to see which one was the best, or and each method performs differently according to because the cosmic web is a multi-scale environment, so you have like very long filaments, and then if you zoom in, you have different, like another kind of filamentary structures, and that's also something that some methods are good to can deal with this multi-scale thing, and other methods cannot do. So he's really trying to understand and to quantify the goodness of of these methods. And actually, there's a paper. I don't know if you're interested in. It's Lipskind. I don't know how to pronounce his name. So in this paper, Lipskind 2018. In this paper, he compares all these different methods on the same galaxy distribution of a simulation, and he does a quantitative study of this.
Yeah, actually, to add something to your question, Jean-Luc, there is not a ground truth you can compare against in these issues, right? I mean, each method carries its own definition of filament. What is a filament at the end? It's also the way you define it. So you cannot really, well, yeah, the idea of comparing different methods of the same simulation is something, because if the methods converge, you're looking at the same object, but otherwise, you're just making up a new definition.
Oh, but you could imagine to have a kind of toy simulation where you have a set of filaments of different size and different width connected by clusters, and then you know the distribution, and you can see how well you recover it.
There's no such thing as a filament. It's open to interpretation what a filament is. But what you can do is, if you want to use, for instance, the filamentary structure for doing parameter inference, you can use whatever definition of filaments you have, and then look at how well you can recover some parameters, some physical parameters. That's a fair thing to do.
Anyway, there is Axel with this hand raised since a while.
Yeah, so maybe just to comment on what you were talking about, I remember I read on the thesis of Aragon Calvo, who work on developing a method to detect filaments. He proposed a method to actually create simulation where you know if a galaxy belongs to a filament with your own definition and a cluster, and like that you can test the accuracy of your methods by knowing the percent of the right classification. But they are not really realistic simulation. They do not depend on cosmology whatsoever, but it's a way to test at least your methods with your definition. But what I wanted to ask is, do you know, when you look at the distribution of short and long filaments, if there is a dependence on redshift or not?
Yeah, so in this study we focused on the local universe, so redshift 0, but there have been some papers that studied so it was not the length of filaments, it was more the radius of what they defined as to be filaments. So it was again with another method to detect the filaments. And there was an evolution. Filaments tend to be thinner with redshift, with time. So today filaments, the same filament would be thinner than at higher redshift. And if I remember correctly, the length of if you have a population of filaments at redshift, I don't know, 5, and today the length of the distribution of length of this population would always be with an exponential tail, whatever the redshift. I don't know if that answers your question.
Yeah, thank you. But I was just wondering if then the property of the filaments are more influenced by large-scale physical phenomenon, like, for example, the expansion of the universe, rather than the actual property of the galaxies that compose the filaments.
This is something that can be tested with doing a redshift analysis.
Okay.
Okay, so if there aren't other questions, let's thank Daniela again for the very nice talk and the very interesting discussion.